So for example, in this case, what's the effective capacitance of this circuit? All right, so this circuit looks really weird, right? I have a 1, 2, 3, 4 capacitor and a straight wire. Okay. So let's see. Let me take care of this wire first. If I want to use a effective resistance, effective capacitor to represent this whole thing, I must simplify this a little bit and then use and try to turn this into some common parallel series example that I already know. So let me try to analyze this. First, I want to take care of this straight wire. What does this straight wire do? It's just a conductor, right? Everything I'm marking in red, they're all conductor, they're just wire. If it's wire, then I can pull them, I can shrink them or elongate them like freely, because it's not gonna affect my potential voltage in any way. So what I'm gonna do is I want to push this side inward. I'm going to shrink the length of the middle wire. So it's gonna look like this. All right. So I push this two end and then push it inward, so it's smaller. Now I want to push it further until this two end touch. And they can touch, there's no problem with that because it's just a conducting wire, right? So it doesn't matter what shape it is. So I will push it up to an end that it will touch. All right, now it touched, right? So from here, you can kind of see this two, C2 and C1, they are in parallel, where C3 and C4 is in parallel. Because C1 and C2, they share the same toe and they share the same head. It's connected by wire and there's nothing between them. So the potential is the same between the heads of the C1, C2 and the same potential between the toes of C1, C2. So now I can replace C1, C2 as effective capacitance. Since it's parallel, since it's parallel. So this capacitance will be C1 plus C2. And then now let's take care of this part. And this part, it's also C3, C4, they're connected in parallel. So I will replace this 2 with the effective capacitance, C3 plus C4. Because in parallel, the effective capacitance is nothing but the sum of them. And now after the simplification, I can easily see these two capacitors, they are connected in series. If they are connected in series, and then I can simplify them and use this effective resistance to represent both of them. And this effective resistance would be like 1 over that effective resistance would be 1 over C1 plus C2 plus C. Okay. So that's it. This is the effective capacitance of this circuit. And you can see to arrive this result, you need to do some imagination and simplification. And the easiest way to do the simplification is to bend the wire in a way that you can see it. Like if this shape looks too weird to you, just try to bend it and bend it to bend it until it's simplified to a case that you can identify. All right, so that's the answer. And how about this case? So this is another example. Determine the charges on the capacitor C1 and the voltage across it. Assuming this is 4 volts. And assuming all this charge they all share the same charge, 3 mu, they all share the same charge. So sorry, they all share the same capacitance. It's 3 mu farad. Okay. All right, so we need to find the charges and the voltage. How do I approach this problem? It seems like we know so little thing, and we need to figure out more than we know. So this is like a puzzle. This is like a puzzle problem. Like you have one piece and you need to connect this piece with its neighboring piece and so on and so forth until in the end you will get a very big picture, a very good picture of what's happening. So let's do that puzzle solving. First, I know this voltage is 4. Let me simplify this first. Okay. So I know these two are parallel, so I'm going to simplify this parallel part first. So because each of them is capacitance is 3 mu, 3 microfarad, 3 microfarad. So the effective capacitance will be the sum of them. So it's gonna be 6 microfarad. This will be 3 microfarad. This is 4V. So I simplify them first. And then what's next? Maybe I can further simplify it. I know these two capacitors, I know these two capacitors, they are connected in series. And since they are connected in series, this effective resistance, this effective capacitance, is 3. So that's gonna be 1/2. So the effective capacitance in this case will be 2 microfarad. All right. If this is 2 microfarad, this is 4V. Then I know what's how much charge will be deposited on these plates, right? Because C equals to Q over V, then charge is CV. So the charge deposit on each plate would be C is 2 mu, where V is 4. So totally it's 8 mu. So totally you will have 8 mu of 8 microcoulomb deposit on each end. And if I know this charge, how does that tell me about the charge across them? So remember this case? If they're connected in series, you can see the charge deposit on the effective capacitor is the same as the charge deposit on each individual capacitor. So based on that idea, if we come back to see this problem, okay, the charge here is 8 mu coulomb. Let me use another color. 8 mu coulomb on this effective capacitor. I'm gonna share the same charge here, 8 mu coulomb. in the 8 mu coulomb. Right. So now we answer our first question. What's the charge on the first capacitor? It's gonna be 8 mu coulomb. And how about the voltage? What's the voltage of the first capacitor? Now we know the capacitance, we know the coulomb. We can find out V by C equals to Q over V. So that V equals to Q over C. Q is 8 mu coulomb, and the C is, how much is C? C is 3 mu farad. So the voltage across the first capacitor would be 8 over 3, which is roughly 2.7. All right, so this is like a puzzle solving. Sometimes, most of the time when you see a complicated circuit like this, you'll be like, oh, what the heck, what should I do now? But start somewhere. You can simplify part of the circuit. You can try to find the effective capacitance or resistance, and then slowly build from one to another. There's a lot of relationship between them, and it's not that complicated. It just takes a lot of practice to get used to this new language.